Welcome. Thank you for joining us today. My name is Dr. Marty Ritchie. I'm with Florida Atlantic University at Harbor Branch Oceanographic Institute. And what I'd like to do today is share with you a study that we did with in collaboration with the Anthropocene Institute and the USDA Agricultural Research Service. And that was looking at the utilization of open formula diets fed to Florida pompano to evaluate microalgae oil substitution for fish oil. Let me go ahead and share my screen with you. Okay, as I said, today I'm going to present utilization of open formula diets fed to Florida pompano to evaluate microalgae oil substitution for fish oil. So to begin with, what I'd like to do is define what open formula is. This is relative to closed formula. So in open formula, you have the entire list of ingredients and the amount of inclusion of those ingredients. So it's totally open and you can replicate it, you can duplicate it, as opposed to closed formula, which is typically what happens with commercial diets, in which by law, they have to list the ingredients in order of their incorporation, but you don't know the levels. So you don't really know what's going on. And I think we'll see the importance of this as we move on. So we had multiple objectives in this study. The first was to evaluate fish meal-free experimental diets relative to a fish meal-based control. The purpose here is fish meal is thought to be unsustainable. We've overfished the oceans and we can't keep harvesting fish to feed fish. So we're looking for alternatives. The second objective was to evaluate algal oil relative to fish oil. So like fish meal, we don't want to harvest the fish to take the oil out of them. So we're looking for something that is completely has no fish in it whatsoever, no marine products. So we looked at soy oil and an algal soy oil blend, and I will explain in a few minutes why this was important. The third objective was to evaluate experimental diets relative to two commercial closed formula diets. Again, closed formula, we don't know what's in them. So people run studies and it's hard to compare data results because we don't know what they have used as a control. And we'll see again in the future here, we'll see why this is important. So when the experiment was designed, we looked at 7 diets. One was a fish meal-based control diet, which is an open formula, which has been used with numerous species so that we have a base on which we can compare. Then there were 4 fish meal-free experimental diets that were similar in formulation to the control diet. And they were all exactly the same. The only difference was the amount of we looked at different oils. So these diets, they had no marine products in them. They were poultry byproduct meal based with spirulina. Spirulina is an algae, which is very high in protein. So we had the 4 oil sources that we looked at: fish oil, algal oil, soy oil, and a blend 50-50 of algal oil and soy oil. The algal oil is very high in EPA and DHA. Then kind of as a co-experiment, we looked at two off-the-shelf commercial diets to see how they compared with each other. So this is the formulation. We see that the experimental diets had no fish meal in them. Fish meal control, of course, did. You had spirulina and poultry byproduct, as I said. Other than that, they were pretty much balanced. So they were formulated to be 46% protein and 16% lipid, which meets the requirements for Florida Pompano. And then we see all the basal ingredients had the vitamins, minerals, etc. So during the experimental trial, we stocked 28 different tanks, 7 treatments, the 5 experimental and the 2 commercial, each with 4 replicates. 20 fish per tank. Starting weight was averaging about 4 to 5 grams. The fish were fed 4 times per day, and they were fed ad libitum. For those new to this concept, ad libitum just means they were given as much as they would eat until they stopped eating. So once they'd reach 5% body weight per day, we stopped. So that was the maximum. They were held at 28 degrees Celsius, a salinity of 34 parts per thousand, and a light dark cycle of 12-12, which is really convenient for here. In the summer, we're 13-11. In the winter, we're 11-13. So this was perfect for our experimental needs. The experiment lasted 85 days. So in terms of data analysis, for objective 1, we looked at evaluating the fish meal control versus the fish meal free diets. So for this, we did a one-way ANOVA, differences tested against the control with Dunnett's t-test. So in other words, what we did was we evaluated each of the diets against the control diet to see how well they did. So we looked at the test for fish meal control against all the other diets with different oil sources. So these are the comparisons that were done. You see the control diet, fish meal based against each of the different oil sources. So what we saw was that the other oil sources, the algal oil and the algal soy blend, performed as well as the fish oil control diet. However, the soy oil performed significantly lower than the fish meal. With that said, the protein productive value was a little bit lower in the others. Significantly, yes, from a biological standpoint, who's to say? So for objective 2, we evaluated diets different only in oil sources, fish oil, algal oil, soy oil, and the algal soy blend. So what we saw, these highlighted in the red were significant differences. So the soy oil performed significantly poorer than fish oil, the algal oil soy blend, and the algal oil as well. Here, in terms of differing only in oil sources, once again, we see that the other oil sources, fish oil, algal oil, and the algal soy blend, performed better than the soy oil diets. So for objective 3, we evaluated experimental diets relative to commercial diets. For this, we used 2 one-sided t-tests, a tossed equivalency test. This is a common approach in the pharmaceutical industry. and is relatively new to the animal nutrition industry. So with this approach, you don't test for differences between the diets. You test for how equivalent they are. So you can look at two different diets and see if your new approach is equivalent enough to you for you to make that leap to a different formulation, depending on the cost benefit. So in order to do this, you have to set the limits. You have to decide what your equivalency interval is. How much are you willing to give up to get the benefit, the cost reduction that you're looking for? So you have to set the bounds. The benefits to this approach is it's user-defined flexibility. So you decide what you're willing to sacrifice for a cost savings. So we'll see here, we chose 10% because we thought that that was the maximum a producer would be willing to give up in terms of production. But you could choose 5, you could choose 7%, you could choose 20%. So there's that built-in flexibility. And it's a powerful decision-making tool because as a producer, it gives you ability to decide what you're willing to accept, what you're willing to sacrifice, and what benefit you're going to get from it. So it puts you in the power. The limitation, though, is in the power sensitivity because it requires a number for us to do this test. And we looked at this as a pilot so that we could collect preliminary data to build on. But it allows you to decide how many replicates you would need in order to get a substantial answer. So in summary, the experimental diets relative to the fish meal control, all of them other than the soy oil were not significantly different. All performance parameters were significantly lower in soy oil fed fish. The algal oil fed fish resulted in a similar protein productive value as the fish meal control. What's really relevant here is that the whole purpose behind doing the algal oil and soy oil blend is the algal oil is more expensive. But by doing the blend, if you can get the same benefit with 50% algal oil and 50% soy oil, which is what we saw, then there's cost reduction in feed costs. So the contrast between diets differing only in supplemental oil addition. All performance parameters were significantly lower in soy oil fish than other supplemented oils. Point 2 is algal oil fed fish resulted in a higher specific growth rate than fish oil or the algal oil, soy oil blend fed fish. Algal oil can substitute for fish oil when substituted at 2/3 of the dietary oil. So in terms of the equivalency test, the TOS equivalency that I mentioned earlier, all non-fish meal experimental diets were tested against the commercial feed 1 and again against commercial feed 2. The tested equivalency for 2 response parameters were chosen, and these were based on production costs, weight gain, and feed conversion ratio. The equivalency interval that we set was 10% because we thought that was the maximum that a producer would be willing to give up for a small cost benefit. So the upper and lower limits were set at 10% of the commercial feed mean. The confidence interval was set at 0.05. So what we see here when we're looking at weight gain, that with the commercial feed 1, that none of the experimental diets performed as well as the commercial feed. We see the equivalence interval set, the dotted lines, at 10%, and none of them even approach that. When we look at commercial feed 1 relative to commercial feed 2, we see that there's a large difference in the performance. So with commercial feed 1, we had much larger gains in weight than we did with commercial feed 2. And this is important because in a lot of feed trials, and why there's so much conflicting information on what the requirements are, is a lot of people use commercial feeds where they don't even know what's in it as their control. And we can see here in terms of growth between the two commercial feeds, we saw a huge difference. So depending on which one of those commercial feeds you choose, you will have differing results. In terms of feed conversion, we see something similar. Again, the 10% interval is set by the dotted lines, and we can see for commercial feed 1, the 10% interval is much lower than it is for the commercial feed 2. In fact, the lower bound for commercial feed 2 coincides with the upper bound for commercial feed 1. Again, underscoring the importance of using different commercial feeds and why it's important to use open formula so that you have a gold standard to test against. In summary, the equivalence test between the experimental diets and the commercial diets. The experimental diets perform below the 10% equivalency interval of CF1. Results of the test against CF2 were a little more equivocal. So again, this underscores the importance of having a known gold standard control to test your diets against. So I would like to acknowledge my co-authors, Rick Barrows, Kelly Alfrey, Zachary Niles, and Paul Wills. And I'd like to acknowledge the support of the Anthropocene Institute and the USDA Agricultural Research Service. Thank you.